See the our presentation now. It is shared, and let me know if you cannot see me. Right. So the last time we discussed about neutron stars, right? And then we discussed how these neutron stars are formed, and then what is a pulsar, how they are discovered, and what is the connection between a pulsar and the neutron star. And we learned that all these pulsars are actually rotating neutron stars, but there are some neutron stars that may not be pulsars, right? So we talked about the formation of pulsars and different properties, how they are created, those stuff, right? And we stop right here uh, about gamma ray bursts. Now this is something that actually not directly related to the neutron star, but just had one slide here. So if you would like to get more details about this gamma ray burst, this is one of the later developments in astronomy for the search of this gamma ray burst. This is actually one of the images that we have in 2008, and there are gamma ray observatories now built in. Uh, and these are actually come from billions of light years away from us. For example, this later observations by large telescopes demonstrates that the burst occurred at a distance of 8 billion light years away, right? So I will not talk more than this about gamma rays due to the time limitations we have. But if anybody is interested, just I have put the links here so that you can go and read about it. Right. So this is what I want to start today, which is the final story of these high mass stars. Right. Now, let me start directly from the word black hole, since this is something that you probably have heard more frequently. Now, for most of this 20th century, the black hole seems to be the stuff of the science fiction, and so they are mentioned as like monster vacuum cleaners. I mean, these some of these statements are wrong, right? So they are not correct, but uh, this is how uh, black hole. This is why black holes are popular actually, and some frictions used to tell you that there are like matter, so there are tunnels between universes, those kind of stuff, right? But we are not going to look at any of these things. What we are looking at today is actually what is actually a black hole is and how it is formed and what are the strange things that can happen around the black hole according to scientific theories, right? So that is what we will talk. uh, Actually black holes are stranger than what these fictions tell, but in a quite different way. uh, so we will discover that the black holes are the key to explain many of the mysteries and the remarkable objects. And so let the image that you see here is actually uh, an image of a black hole in the left hand side, and this is a stellar mass black hole, which indicates you that there are different types of black holes, right? In the left hand image is what you see from a visible image, which means if you go to a optical telescope and get a picture, this is what you see, right? So this is basically that red square that you see in this left hand side image is the place where you have a black hole, and this is in the constellation Cygnus. And actually, the reason that we used to tell that there is a black hole in that particular position is that there is a bright X-ray source that you can detect from X-ray telescopes, right? So that X-ray source we used to name as Cygnus X1, and this is actually an example for a black hole created when a massive star collapses at the end of its lifetime, right? And this is exactly what will happen to a star when its mass is higher than a particular value. This is what will happen, right? Now, as you see here in the left hand image, it is you cannot like tell from these optical images that there is a black hole, right? So what we have is on that particular location from this red square, there is a bright X-ray source that you can detect from X-ray telescope, so that we know that there is a black hole at that particular position. The reason is, as you see in the right hand image, the the image is actually not a real image. This is an uh, artistic impression about a black hole. This is this black circular shape right here is what he has drawn as the black hole. And then what the black hole can do is that it can take or accrete material from a surrounding star, right? So here is the surrounding a nearby star, uh, and we used to tell that this is a blue companion star. So the materials, uh, so the black hole, what black hole does is it pulls all the material away from this massive blue companion star, and this material will start to, uh, excuse me, this material will start to swirl away around this particular black hole, right? And they will get heated up, and there is a point that they can emit X-ray as a result of that. And this X-ray is what we detect from X-ray telescopes, and this is kind of an indirect way of telling that there is a black hole at this particular position, right? So these are just uh, an indirect evidences that we can tell that there are black holes. Uh, Now let's see what actually happens. Right? Now remember that the last time when we discussed about the neutron stars, the neutron stars came as a result of neutron degenerate pressure. Right? Now remember we had three things that can happen, two things that can happen to a star up to this point. If a star is a low mass star, that particular star will become a white dwarf at the end of its lifetime. Right? And if a star is a high mass star, then that particular star can finish its life as a neutron star. Remember that we how we had a neutron star, right? So you have this neutron degenerate pressure at the central region of the star, and then when the material is collapsing, so those collapsed materials will be halted and bounce back towards the outward region again with these shock waves, which will create these type 2 supernova. And as after the supernova, the remaining core with densely packed neutrons will give you a neutron star, right? But there is one more possible end state to a star, that is a black hole, right? Now, what happens is if this the neutron star has a mass greater than three solar masses, right? Remember the neutron stars, we did not specify a mass. Uh, so if you have a neutron stars that have masses greater than three solar masses, then what will happen is this neutron degenerate pressure cannot support against the gravity because of this high mass, right? If the neutron star has a mass greater than three solar mass, what happens is the gravity is larger or higher, so that the neutron degenerate pressure cannot hold the collapsing, right? So this is what actually happens. Now, when this happens, there is nothing actually to stop the collapsing of the star towards the central region, right? So what will happen is then these objects will overcome the pressure from their neutrons and will collapse further, right? So once again, what happens is when a neutron star has a mass greater than 3 solar masses, the core of the star, which generate the neutron, the neutron degenerate pressure cannot support against the gravity because of the higher mass. Then the whole star will continue to collapse because the neutron degenerate pressure cannot stop it, right? And then what will happen is, now all the situations that we talked up to now, there will be something at the center that can hold it, right? Step by step. Remember, the white dwarf's gravitational collapse is at the end is halted by the electron degenerate pressure, so which means it will stop at some particular point. And for the neutron stars, neutron degenerate pressure will stop the gravitational collapse, and then uh, all this material will be bounced back after that. Right? But when the mass is even higher, what will happen is even the neutron degenerate pressure cannot stop this gravitational collapse, right? So which means now you know that after the neutron, there is nothing that you can stop this gravitational collapse inside the star, right? Now because of that, this will squeeze all the star matter down to an extremely tiny volume of space, right? Since there is nothing to stop it, all the matter in the star will be uh, squeezed to an extremely tiny volume of space, right? Now, what this means is the density will be extremely high. Right? So these are like unthinkable densities. Now, as a consequence of this, the light will be unable to escape from the inner regions of this collapsing star, right? Now, this is why these dense objects are called black holes, because even the light cannot uh, escape from that. And the reason you will see in the next few slides when we learn about the basic concepts about the general relativity, we will discuss why actually the light cannot escape, right? Because under normal theories that we know light should travel in a straight line, there should not be a problem for the light or any effect for the lights under any thing that happens due to gravity, right? But you will realize that that is not the case in this when you have very huge masses, right? Now, at the same time, many other unfamiliar phenomena occur in these regions when you have extremely high density, right? And these things are actually predicted by Einstein's theory of relativity. Now, this is why we will learn about a bit about the relativity theories. Remember that we will not go into equations and derive everything like that, right? That's kind of out of the scope in this particular class. So I will basically explain you the very basic concepts and how they are related to these different phenomena that happens in the black holes. Right? So that's all I want to discuss in this class. Right. So I hope everyone is clear up to now about the black holes, how black hole is formed, right? This is just one stage, uh, and in fact is the final stage that can have a very heavy mass star. Uh, that is, if the neutron star mass is greater than 3 solar masses, then the gravity overcomes the neutron degenerate pressure. Then there is nothing to stop that. Because of that, all the mass will be squeezed into a very tiny volume. And as a result of that, I just stated that even the light cannot escape from that. And this is why we have this name called the black hole. Now let's look at a little bit in detail what actually happens. And before we go into that section, we just need to have a very brief introduction about the black holes and sorry, about the relativity. Now, just give me a minute to go into next slide. Yes. Now, when we talk about the relativity, there are two theories in relativity. The first one is called special theory of relativity, and this is introduced by This famous physicist called Albert Einstein. I guess all of you know about it. And this happens early in the 20th century. And this first theory that he has introduced in 1905 is called special theory of relativity. And what he has basically mentioned there is actually the theory basically applies for objects that are not accelerating, right? So that is the important point here. So the theory in the special relativity is for objects that are in moving in constant velocities, right? Not accelerating, right? Now, the first principle that he states is that the laws of motion and physics will be the same for all frames. I mean, all of you know about this. And the second principle is that when we measure the speed of the light, it is a constant, about 300,000 kilometers per second in a vacuum. And this will not change from observer to observer, right? These are the two principles that he has introduced. And so if I give you an example for that, now if you imagine that you are traveling in a car, let's say at 100 kilometers per hour, and then you fire a gun in your direction of travel. So while you are inside the car that is traveling at 100 kilometers per hour, you will fire a gun in your direction of travel, right, to the same direction that you are traveling. Now the bullet leaving the gun, assume that it has a speed of 1000 kilometers per hour, right? So it is 10 times faster than your car, right? Now the final result will be the bullet will be moving at a speed of 1100 kilometers per hour in the frame of reference of the road. So if you are on the road and looking at this bullet, so what you will calculate is that the bullet is moving at a speed of 1100 kilometers per hour, right? So this should make sense for you, because this is what we will do to calculate the relative velocity, right? So you have these equations, and you can, even without equations, you know that how to calculate the speed of an object with relative to another object, right? This is the normal situation. However, now you if imagine the same situation, that you shine a light from your car in the direction of travel. Now this, for example, let's say you are traveling on a car or a motorbike, and you switch on your headlight suddenly, right? So then uh, you have a light, right? Now you know that the light has its speed, let's say 300,000 kilometers per hour, as I have mentioned. Now, under the if you consider the same situation, then your prediction will be that the light will travel at a speed of 300,000 kilometers per hour plus 100 kilometers per hour. So you have to adapt these two velocities, right, according to normal way of finding relative velocities. But what Einstein stated is that this is not true. So what he mentioned is that the speed of the light will not change depending on the reference frame. It doesn't matter whether you look at the light from the car, or whether you look at it from the road, you will still get the same speed. So that is the speed of light. So that's what he has stated as the speed of light is a constant, right? So that is basically what Einstein introduced in his theory of special relativity. And after 10 years, in 1915, he introduced his revolutionary theory of general relativity, right? Now, this general relativity actually includes the effects of gravity. Now, this is why it is important in astronomy. Right? So, incorporate the effects coming from the gravity into the theory, and this new theory of general relativity actually explains how the space and time are related to one another, how the space and the time is related to each other, right? Now, he stated that the space and the time can no longer be treated separately, so they are related to each other. Now, uh, so what he stated is that when you have a massive object, it actually curve the space surrounding it, right? So if you have a very massive object, it will curve the space, and as a result of this, it will change the path of the other objects nearby, right? So think about that you have a very massive object, and this object curved the space, and then any object that is nearby have to travel on this curved space, right? So which means naturally the path of that particular object will be changed due to this effect, right? And you can explain from this curvature of the space-time, you can actually explain why planets orbit around the sun. And we know that the planets orbits around the sun can be explained using Kepler's laws, right? So that's what we learned. But it can be precisely explained using this curvature of space-time from the general theory of relativity. And also it explains the force of gravity, which is actually the general relativity explain it as not as a first force but as a cur- curvature of the space-time, right? And the path of the light is also affected in the same way, right? So once you know that when the space is curved, the light will be, and light will not follow a straight line, right? It will be bended as well because of the curvature of the space. And also these massive objects will cause the time to slow down, right? Now, this is another effect very close that happens very close to the black hole. The times run slowest close to very massive objects. Now we know that these black holes are very massive objects, so the time will run slower close to these massive objects, right? So these are the things uh, basically that he introduced in the general theory of relativity. Now, this is a few examples how it looks like. Now, in this particular figure, you have a heavy mass at the center right here. And once you keep a heavy mass, the surface around it is curved, right? If not, it would be a flat surface, right? But when you keep a mass, the surface curved around. Now, this can be interpreted from a very simple example. Think about you take a blanket, a bit larger blanket, and then you attach four ropes into the four corners of the blanket, and then you stretch it and make a flat surface using a blanket, right? And then what would happen if you jump into the middle of that particular blanket, or if you keep a heavy ball or something like that on the center of the blanket? So then what will happen is the blanket will curve, right? And this curvature will be higher close to the mass that you put at the center, and it will be like smaller when you go away from that particular point from the blanket where you have the mass, right? So you can actually do this small experiment at your home, and you probably know about this, and interpret this same effect that matter curves the space. Now here is an example actually what happens when this curvature uh, is taken place. And in this left hand, so this is something similar to what I have just explained. In this left hand image, you have a rubber sheet that you put on a table, and there is an ant that is moving in a straight line, right? So on this rubber sheet, if you have a trained ant, it will not have any trouble walking in a straight line if you trained uh, the creature to walk in that way, right? But in the right hand image, however, that if you put a little bit heavy uh, object at the center of the rubber sheets. I mean, since this is a rubber sheet, even a small, a little bit like a small paper weight should be enough to do that. So once you keep something heavy at the center, what will happen is that particular region will go down. Right? This is a rubber sheet now. So rubber sheet is like you can assume that as the space, and then because of the heavy mass, the space will be curved, right? And then what happens to the end is then now he has trained to go in a straight line on the space, right? Since the space curved, he will automatically follow this path. He go down and come like that, right? So his path is also curved, right? So that's what I have mentioned that because when massive object creates a big depression in the sheet, the ant which must walk where the sheep takes it, find its path changed dramatically. So he thinks that the ant thinks that he is following a straight line, but he has to go in a path where the sheep takes him, right? Because he is traveling on the sheet. If the sheet is curved, it has to take it. I mean, he has to take that particular path. So that's an effect of the general relativity, and also this is what we explained earlier. What happens to the light due to this particular effect? Now, in these two images, in the left-hand image, which I named as A, which is this one right here, is actually that suppose that you have a person that can stand on the surface of a normal star, right? So let's say this particular person is standing on a star, right? And he has a flashlight in his hand, and then he lit up this flashlight, and then look at how the light travels, right? Now, the light leaving in according to the figure A, the light leaving the flashlight travel in a straight line, no matter where the flashlight is pointed, right? So it doesn't matter where this is pointed, you know that the light will be distributed equally among all the directions, and they will travel in a straight line, right? So this is what we know up to now. Now, think that this is a very massive star, and this star collapses, and now the size of the star becomes little larger than the black hole. It's not a black hole, but it will be very close to a black hole, right? So if the size collapses, and it has a very high dense object which is very close to a black hole, and that's what you can see in the right hand image, right? Now what will happen is then all the light paths except the one straight up curve back to the surface. Since this there is a high dense object, all the space around it curved, and the curvature is so high that except this one light beam that's straight right here, all the other light beams will curve back towards the surface, right? So that's what happens as a result of this general theory of relativity, right? Now, think that this star will further shrinks and further will become more and more smaller and become a black hole. And in a black hole, there is something called an event horizon, which we will discuss. That is the like the outer like the boundary of a black hole. And so, if this particular star shrinks inside this event horizon, even this beam right here will not come out, right? So that will be, which is directed up, straight up, will return again, right? So even that light beam will not come out. Now this is exactly what happens when you, for a black hole, and this is why we used to tell that the light even do not escape from a black hole, right? So that is due to this huge curvature of the space, uh, so that the light cannot even escape from it, right? Now, this as a consequence of this theory of general relativity, there are four main effects that specifically will happen close to a black hole, right? So those four effects I have mentioned here. The first one is we called as time dilation, and the second one I called as the gravitational redshift, and there is something called event horizon for a black hole, and the fourth one is tidal effects, right? So I will discuss these four effects mainly about the black hole. Now the first one is time dilation. So what uh, that means is the curvature of now if you consider the uh, black hole, the curvature of the space near the black hole has this effect of slowing the time itself, and this is what we called as the time dilation, right? Now I will not prove you that how this is happens, but I will just explain the phenomena behind that, right? Now suppose that you, so let's think it in this way. Assume that you convince to a friend that you ask your friend to travel towards a black hole with a giant clock with him, right? So you ask your friend to travel near to a black hole with the clock, right? Now, what you would notice is that the, their clock would actually slow down relative to your time. So you are measuring it from here, and relative to you, your friend's clock will actually slow down, right? But your friend will not feel this time slowing down, right? So it is you that will see that his time slows down, right? Now as your friend approach to the event horizon, now event horizon I will discuss. Event horizon is like the boundary or a region where there is a special limit that we have for the event horizon, where you once you cross the event horizon you can't come back in the black hole, right? So that is the idea behind that. You will see that uh, when it when the your friend approach to this closer to the event horizon of the black hole, which is like the boundary, the time slow down more and more for him, right? And so the amount of slowness is that you will never see them cross the event horizon, right? You will not see it because it gets slow down and slow down and slow down, and you will not see that he is crossing that particular boundary, which is the event horizon. However, your friend will experience a rapid crossing of the event horizon. So he will feel that he just crossed the event horizon and plunged towards the black hole, right? So this is what happens under the time dilation. And actually, there are ways that you can prove it. So you probably need to do this Einstein equations and then have to prove that about this time dilation equation, and you can actually calculate these things. But I mean, depending on the context of in the context of this course, I expect from you that this general idea behind it, right? Right. Now, this is one good example for this time dilation due to the general theory of relativity. This is actually not close to the black hole, but this is something that we can experience when you transmit these electromagnetic waves in space. Now, probably you have heard this Viking probe, which is actually sent to Mars, one of our planets, and it actually sends us radio signals. So what happens is when this Viking send us radio signals from Mars, it has to come through the space, and there is a point that it goes very close to the sun. So what happens is due to the gravity of the sun, the space around the sun is curved considerable amount, right? Because of that, the Viking will the radio waves will follow this path, this curved path like that, and due to that, that there is a time delay of receiving this signal, right? And that's what I have mentioned here. According to the general theory, general relativity, there would be a delay because the radio wave would be passing through a region where time ran more slowly. It's basically because of this curvature of the space, right? So the experiment was able to confirm the Einstein theory to within 0.1% accuracy, right? So these are the experiments that actually have proved that Einstein is correct, because in 1915 when he was introducing this theory, there were no experiments. It is just a theoretical explanation that he gave us based on the knowledge that he has, right? So that is why he is considered as one of the greatest scientists that we ever had, because even without any instruments and anything like that, he has predicted all these things in his theories. It is now that we know that it is correct, right? By having these experiments, because you can't test a theory like the general theory of relativity under normal circumstances in our day-to-day life, right? So that's about the uh, this time delay, and let's see what is gravitational redshift, right? Now remember that there are different types of redshifts that we used to discuss. Maybe we have discussed Doppler redshift before. If not, at least you probably have discussed in your other physics classes. Even in sometimes in the advanced level physics, you used to discuss this Doppler effect for sound, and the same effect will be applicable for uh, light waves as well, right? All the other electromagnetic spectrum, the same thing will apply, so that you will have a Doppler redshift when you have something moving away from us, right? So that is called Doppler redshift. But what we are talking here is not that, and this is a different redshift, and this is called gravitational redshift. This is basically due to the effect that coming from these huge masses, right? Now suppose that you have a bright object located very close to a black hole, right? Now the light leaving this object will lose the energy as it move away from the black hole. Now this is basically due to this curvature of the space-time, right? Remember I told you that the light waves are curved because of the curvature of the space by the black hole, right? Due to this effect, the light coming out will lose its energy, right? Now the one, when the light loses its energy, uh, all these light waves will be redshifted because of that. But just think about that, when losing energy, what happened to this wavelength and everything, right? You know that energy equal h over lambda, so that when energy reduce, the lambda will increase. You can think about that, right? So that the light waves will be moved to this redshift range, or basically they will be redshifted, right? Which means the light uh, will go, these light photons will be shifted to longer wavelength. So that's why we used to tell that they are redshifted, right? It happens for all the waves in the electromagnetic spectrum, right? You see that once the reason is actually that when you lose the energy, energy is given from E equal h over lambda. So when energy is reduced, the lambda should be increased, right? The wavelength should be increased. Because of that, all the wavelengths will be shifted towards the redder wavelength direction, right? So that's what we called as the gravitational redshift, and this happens due to this curvature of the space-time. Now, light that is not moving directly away from the black hole will have its path curved towards the black hole, right? Now, if the object is close enough to the black hole, none of its light even will be able to escape from the black hole, right? And that is what we called as infinitely redshift, right? So just understand what happens here and make sure that you differentiate this particular situation from the Doppler redshift, right? Doppler redshift is another thing. This happens basically due to these huge masses, and these masses curve the space-time so that the the light escaping will lose its energy, which made them to shift it towards these larger wavelengths, right? So once again, you have the same uh, uh, image just to make that connection. And then let's look at this word called the event horizon, right? So I just escaped it up to now. So we discussed about the time dilation near a black hole and this gravitational redshift. Now I am going to talk about the event horizon of a black hole. So event horizon of a black hole is that, uh, so I told you that the gravitational redshift is very strong close to a black hole. And in fact, now these all of these black holes, they have a precise region which light is unable to escape, right? So there is a point that beyond that point even the light cannot escape, right? And this particular region or the point is what we called as the event horizon of a black hole, right? Now there are few, actually we can calculate this event horizon using very simple physics equations. Now distance from the center of the black hole to its event horizon is called as the Schwarzschild radius. Now I expect that you know about these things, right? So these are very basic things that you can do using just basic physics, right? So first you need to know what is event horizon. Event horizon is the region where the light is unable to escape, right? So that's a particular point. And the distance from the center of the black hole towards the event horizon is what we called as Schwarzschild radius, right? So these words are actually coming from this the proofs of the general theory of relativity, but I expect that you will, when I say Schwarzschild radius, you should be able to identify it, right? These are probably new words for you. Actually, this does not refer to the actual size of the black hole, right? Since its matter has collapsed down into the center, this is just a region, right? That even the light cannot escape. And the size of the Schwarzschild radius is directly proportional to the mass of the black hole. Now, this is the property that we need to understand. If the mass is higher, the Schwarzschild radius is higher, right? If the mass is lower, the Schwarzschild radius is smaller, right? For example, if you have a black hole mass with three solar masses, so by the way, this there is a small correction that I want to mention here. This should be actually solar masses, right? So there is a question mark here for some reason that maybe the equations is not written correctly. This should be actually three solar masses. Now, if you have a three solar mass black hole, then the Schwarzschild radius, which I usually denote from RS, is about 9 kilometers, right? So which means you can, if you have a black hole which has a Schwarzschild radius of 9 kilometers, you can go as close as 9 kilometers to this particular black hole, but if you proceed, then you cannot come back, right? So it's something like that, right? Is this Schwarzschild radius is given from this simple equation. Now, I expect from you to remember this equation, right? If not, actually, you can derive this equation in the same way how you derive this escape velocity equation in Newton's gravitational theory by equating energies, right? So it's up to you whether you can figure it out how to prove it, or you can remember it, right? So we will be using this equation even in exams, and because of that I expect that you will remember this equation, right? This is like a basic equation. And this Schwarzschild radius is given by 2 times gm over c squared. um, Let me just give me a minute. I guess there should be a square root here, so just give me a minute, I need to check this. Right. So I guess it's okay. The equation is correct, right? So it's the other equation that I had. Just forget that. Right. So that's correct. Right. So I guess you can again see my screen right here. Now here G is the gravitational constant and M is the mass of the black hole and C is the speed of light, right? Now I would like that you answer these two questions as we have a limited time now, so I'm not going to take the class time for this one, but here are two examples that you can try and make sure that you actually try this and find the answers. The first question is actually about this Sagittarius A, which is actually the astronomers have traced the path of several stars near the center of our galaxy and found that they seems to be orbiting an unseen object. Right? We will discuss further more about detecting black holes about this Sagittarius A. What actually has happened is close to the center of our galaxy, astronomers have detected this one few stars that are rotating around a particular star that should have 4 million solar masses, but we have never detected, astronomers have not detected it at that particular time. And this is actually, we believe, as the supermassive black hole that we have at the center of the our galaxy. Now, since we have predicted the amount of mass of this particular object, we can find the Schwarzschild radius of that by substituting the values into this equation given here, right? So this equation right here, use this equation to calculate that, right? At the same time, I just gave you the an example which is a bit unreal. That is, uh, if you consider a typical truck with a with a mass of 3,000 kilograms, then you can just think about what would be the Schwarzschild radius for that, right? So, and you will see that this is why this effect is not that much considerable in our day-to-day life, right? So it's the same type of calculations, but practice it for these two questions, which I will take those questions later if I get time, but just try yourself. It is just that you have to plug the values into that equation, right? So that's it. Now, this is another example of the application of uh, general theory of relativity in practice, right? And this is called Mercury's wobble. And you know that Mercury is one of the closest planets to the Earth. Not one of the actually. This is the actually the closest planet to the Earth, and the Sun is at the center right here. And there is an observation that we have for a long time that this wobble of the Mercury's orbit. That means the Mercury does not follow the same orbit. When it comes to the next round, the orbit has changed a little bit like that. And the next time it will go like this. So there is a wobble. We call this as a wobble of the Mercury's orbit. Right? There is a small wobble in the orbit, which actually we cannot explain by the Kepler's laws, and also there is something called perturbation theory. When you have these small changes, you can actually calculate those changes using these small perturbations which are coming from the effect from the other planets, right? You know that in the solar system it is not only Mercury and Sun, or even though we consider those two objects for the calculations in the Kepler's law, there are other planets that moving around. So these gravitational effects of those planets also should be taken into account if you need to do a precise calculation, right? So when you take those into account, we used to tell that those are as perturbation effects. So we have astronomers actually have tried even with those perturbation effect to check whether they can predict this effect, but they could not. And later, this cause, the reason is actually this the wobble is even larger than uh, these perturbation effects. Basically, if you do the calculation using the perturbation effect, it is not that much, and this wobble is even greater than that. And the reason uh, later identified, this is because of uh, the curvature of the space time near the sun. So that is what has happened, and this was very accurately calculated then by the theory of general relativity. Right? So that's what I have mentioned here. The major axis of the orbit of planet, such as Mercury, rotates in space slightly because of various perturbations. Right? In Mercury's case, the amount of rotation is bit larger than that can be accounted for gravitational by the gravitational forces exerted by other planets. So that's what I discussed. And this difference is precisely explained by the general theory of relativity. Right? And then Mercury, being the planet closest to the Sun, has its orbit most affected by the warping of the space-time, because this Mercury is very close to Sun. The curvature of the space-time due to the Sun is mostly affected to that particular planet, right? Because this curvature is higher close to the Sun, right? And this is predicted by general theory of relativity. And here is another effect that we can discuss. Now, here is the curvature of the light, because we assume normally that the light would travel in a straight line. Now, if I explain this very briefly, what we have here is that normally light used to travel in a straight line as you see here. And because if you have a sun nearby, then what will happen? So that will cause a curvature like this for the path of the light, right? And because of that, our apparent direction of the star and the actual direction will be changed, right? That is because of the deflection of the starlight due to these huge masses that curves the space, right? Now, it is true that up to here that everything that we discuss are actually the uh, effects that comes into these objects in astronomy, right? For example, from the sun for the black hole and those kind of huge objects. Now, does this mean that there is no use of this general relativity for our day-to-day life? Is it applicable even for anything other than these objects? Actually, if you read through this slide, which is a bit wordy, but I wanted to put everything here just to give you an idea about how this theory of relativity is affecting to our day-to-day life, even we don't think about that. So this whole thing that I have explained here is about your Google Maps, basically, right? So I just want to mention this application for you. Now, the GPS system is what these all these mapping systems are used, mapping these Google, especially the Google Map that I would like to talk, and there are other navigation systems. So they basically relies on GPS, and GPS work using these 24 satellites that are orbiting around the Earth, right? At least 4 of them are visible from any spot on the Earth. So that's how it works. So they carry a very precise atomic clock, right? So atomic clocks are the most accurate clocks we have in our world. The clocks on the satellites are orbiting Earth at a speed of 14,000 kilometers per hour and are moving much faster than clocks on the surface of the Earth, because they are moving 14,000 kilometers per every hour. These clocks will get affected because of these movements, right? Now, special theory of relativity, which introduced by Einstein in 1905, it says, according to this special theory of relativity, these clocks on the satellites are ticking more slowly than the Earth-based clocks. right? And this amount of the slowness is actually 7 millions of a second per day. So every day, 7 millions of a second, there will be a difference between clocks that we have on our Earth and in these satellites. And this effect comes only from the special theory of relativity, right? However, these satellites are also orbiting around the Earth, and they are normally located around 20,000 kilometers above the Earth, right? So what will happen is gravity is about 4 times weaker in those in that orbit, right? Because there is a 20,000 kilometer difference, and because of that, the general relativity also will come into play, right? So what happens is, since the gravitational effect from the Earth is smaller for these clocks inside these satellites, they will tick about 45 millions of a second faster than they would on Earth, right? So there are two effects that coming from the special theory of relativity and also from the general relativity of theory of relativity. Now, if you combine both these effects, the net effect is the time on the satellite of the clock advances by about 38 microseconds per day. Now, it seems like this is not that much, right, that you have to consider in day-to-day life. But what actually happens is, assume that you did not take this amount of change into consideration, then what will happen is the navigational errors, for example, in your Google Maps, this error will add up and positions would be off by about 7 miles in only one single day, right? So think about, we will not go into these calculations, but this is why these relativistic theories are important, right? Sometimes students think that nobody is using these things, but on real situations, actually people are using those for calculations. If not, all of your coordinates will be completely wrong, right? Think about the difference of 7 miles in one day, right? 7 miles means how many kilometers? It's around 12 kilometers, right? So that is just a perfect application of this theory of relativity in day-to-day life. So let me quickly go to the next sections. Uh, Now, we talked about the black holes, and we talked about the theory of relativity after that, especially about the general theory of relativity. And then combining the general theory of relativity with the black holes, we discussed about the four basic effects that you can see close to a black hole. Those are the time dilation, and then gravitational redshift, and the event horizon. And there is one called actually the tidal effects, which I this we did not discuss much, but let me see. Yes, the tidal effect is basically due to these huge curvatures that you will have different gravitational effects on the two sides, even for a small star, right? So which can lead to torn apart all the materials inside that. Let's put it in that way, right? And now for the black holes, the black how black holes are formed is actually what we discussed previously is about what happened to these how these stellar mass black holes are created, right? That's what we have discussed. But that those are not the only type of black holes that are available in the universe, right? So stellar mass black holes is what we discussed previously during our star formation process. So that happens basically for high mass stars when a neutron star is created, and if it's the mass of the neutron star is greater than 3 solar masses, then it will lead to these stellar mass black holes. But there are other types of black holes. There is another type called primordial black holes, which may have formed during the early stages of the universe itself, right? But we have not detected those, but we predict that they will be there, right? And then there is another type called supermassive black holes. And these black holes normally form in the centers of the galaxies. And the reason that we call them as supermassive black holes is that they may contain millions or billions of solar masses, right? And we will briefly discuss about supermassive black holes if we get time in the sections about the galaxies, right? Because every galaxy has a supermassive black hole at the center of its, I mean, at the center of the galaxy. And then there is another type called intermediate mass black holes. They form in other ways, like basically by merging of two stellar mass black holes, right? So those things can happen. Right. So this is what I actually one thing that I did not discuss before, that is the tidal effects, which I explained to you. So what happens is where the tidal effects means if you have an object, let's say a star close to a black hole, it will feel this gravitational pull from the black hole, right? Now, part of the star that is closest to a black hole will feel a stronger pull than the part that is further away. And this difference is so high that can create these tidal effects, right? So, because of the tidal effects, the star, one side of the star can stretch more compared to the other side, right? Now, if this star is closer enough, then to the black hole, so what could happen is the star might be torn apart completely, right? And I have, if you need like more details, I have a small YouTube link right here. So I will be uploading this presentation soon so that you can go and look at it, right? So those are actually the details about the properties about the black holes. Now the next section is about uh, whether black holes actually exist, right? So that's what I am trying to explain here, right? So we discuss about how black holes are formed and different phenomena close to the black holes using this general and special theories of relativity, and then the effects uh, of the black holes. And then the question now we have, everyone should have, is that uh, can we actually see a black hole, right? Because the theory, according to theories, we tell that the black holes exist, and we have discussed how they are formed according to these star formation theories. Now the next question should be, do they actually exist? Because I have not shown you a black hole, right? we I saw you that in this location there could be a black hole, like those kind of things, but we have not seen a black hole actually, right? The question should be, do they actually exist? Right. So before I start this, if anybody have any questions up to here that you need to ask before since we talked around 1 hour now. Right. So if anyone do not have a question, so let me start talking about this particular section. Do these black holes actually exist? Right. Now, we know that the light doesn't escape from the black holes, right? Which means black holes cannot be seen directly since the light is unable to escape from them, right? However, if the material that is being pulled down into a black hole may be tidally heated, so these, once the materials is pulled down towards the black hole, they get heated. Once they are heated into these higher temperatures, then this gas can radiate X-rays, so that they will give off X-rays close to a black hole, right? And this is probably one way of detecting it in X-ray region or using X-ray telescopes. And the other thing is black holes, since they have these huge gravitational pulls, the closing stellar neighbors should affecting this, which means if you have a very huge black hole and then there are some stars uh, that are close to this particular black hole, the effects coming from the black hole due to its huge gravitational pulls should be seen by the motions of these nearby stars, right? Now, this is how actually we have detected there are like supermassive black holes at the center of our galaxy in the first point. And also there are some binary star systems. One of the example is the Cygnus X1. It has one visible star plus a companion star which can be only seen in X-rays, right? That is a good evidence that we can probably assume that this invisible star that emit X-rays should be a black hole, right? So these are the normal general ways that we normally estimate that there could be a black hole at a certain point. Now this is the discovery about the stellar mass black holes, and this is a binary black hole, and the picture that you see not an actual image, that's an artistic one of the images that drawn by an artist to show a black hole, and there is a red star nearby. When the matter, so you can see that, let me take the laser here, right? So when the matter is pulled towards the black hole, so they get heated up, and because they are heated up some, and then they will start, the black hole will start to emit X-rays into the perpendicular directions, right? Now, detecting those X-rays, you can sometimes predict that there will be a black hole, and this is an example like that, a black hole detected, and this image is taken from the one of these NASA websites, and I have put the link here so that you can go and read about the particular story, right? And there is a small diagram right here on the right hand side. Also there is a star that all the material from this star is attracted by the black hole right here, and once they get heated up they will emit these X-rays. So once you detect X-rays, then you can conclude that there may be a black hole right here, right? So that is one way of detecting black holes, right? Now this is the object that we discussed in that one of the previous examples that you can go and look at it. And this particular star, which we called as Sagittarius A, is actually what you have at the center of our own galaxy. And now astronomers have looked at some of these stars at the immediate vicinity of this Sagittarius A within the distance up to 30 light days, right? Not light years. And all these stars actually have these kind of orbits that when they are close to the center of the black hole, they move very fast, right? So which means there should be, now to have this effect for all these stars, there should be a very huge mass at the center of the our galaxy, right? So this is another way of looking at or predicting that there may be black holes, right? So that's another way. I mean, these are like basic physics theories that you already know, right? You can, once you know the the circular motion of one object, you can predict what is at the center, right? What kind of force exerting by this central mass or the mass of the central object. So that's what we are using here. Right. So all these things are actually indirect observations, which means you are not observing something uh, as an effect from the direct effect from the black hole, right? Now, so this is what you had until 2016, which is probably 5 years ago now. But now we have direct observations from black holes, which is again actually predicted by Albert Einstein in his general theory of relativity, right? According to the general theory of relativity, he has actually predicted that any arrangement of matter. For example, let's say that you have a sphere, and then if this matter is rearranged to, let's say, a sausage shape, just to understand, this will create a disturbance in the space-time because of this, the rearrangement of the matter, or the change in the matter. So it will create a disturbance in the space-time. And this disturbance is called a gravitational wave, right? So that this is what Einstein predicted. And so he predicted that these gravitational waves should spread outward at the speed of light, right? For example, let's say you have a merge of two black holes. So they, once they merge, they will considerably disturb the space-time, which will create these gravitational waves. And these gravitational waves should be spread to the outward directions with the speed of light. So that's what he actually has predicted. Now, the challenge that the astronomers had was these waves are actually very weak. So they are tremendously weak that these than electromagnetic waves. Now we know the electromagnetic waves very well, right? We know the electromagnetic spectrum and different parts of the spectrums like X-rays, gamma rays, visible light, radio waves. All those stuff we know, right? And we can detect those. But the problem with the gravitational waves is that these gravitational waves are not in the electromagnetic wave spectrum, so they are completely new, and at the same time they are tremendously weaker compared to the electromagnetic wave. Now, since they are weaker, it is very hard to detect them from Earth, right? We did not have any kind of instrument to detect those, right? Now, according to these theoretical calculations, the sum of the most likely events that will give this kind of gravitational waves are actually maybe merge of two neutron stars. So these huge events, right? And then swallowing of a neutron star by a black hole, or maybe merger of two black holes. So these are the events that can actually create at least a considerable amount of, I mean, not considerable amount, strong enough gravitational waves that we may be able to detect from Earth. So astronomers actually worked very hard on this for last 4 decades to develop an instrument or an experiment that can detect these gravitational waves, right? And this is what we call as laser interferometer gravitational wave observatory, or LIGO, right? So you may have heard this about this now. Probably it was in the news in past few years because they detected these gravitational waves from this new instrument. And the actually building up this new instrument is not as easy as you think. This is like a super sensitive instrument that took like decades to build up by making corrections and those kind of things, and the huge amount of money is put on this as well. And this is this gravitational wave telescope. It is, even though you tell it as a telescope, it is actually not a usual telescope that you would think. This is something very similar to interferometer, which means you send up. It has very two long paths to this direction. There is one path and there is another path to this direction, and these are like few kilometers long. And what would happen is, if you have like a change in the space time, one of these paths, so they have a laser beam that goes into this direction and comes again to the same location, and there is another laser beam that go in this direction and comes to the same location, and they are synchronized in such a way that they do not have a phase difference, or they do have a phase difference. And then if it detects a gravitational wave, that means this disturbance of the space time, then there will be a result as a change in this interference pattern created by these two uh, laser beams, right? So that's, in brief, that's what can happen. And by the way, this interference pattern should be come from the outer space, from black holes or something like that. And because of that, they have isolated this particular the whole instrument from the other things that can affect for this. For example, even in the nearby highway, there is a truck going on. These small disturbances could affect and make interference patterns here, right? So they have isolated all these things from this experiment. Now, on 11th February in 2016, for the first time in the history, so they have detected these gravitational waves from merging of two black holes, right? And now we have the information about those two black holes as well. So they have found that the gravitational waves produced by the merger of these two black holes, and even the mass of the black holes have also counted now. One black hole was 20 solar mass and the other one was 36 times the solar mass. So how they are calculated is actually a different story, because you need to know all these theories. But just so I'm just providing the information here only. And this merge has happened 1.3 billion years ago, and then this has actually converted uh, energy that will equal to 3 times the mass of the sun. You can see the amount of energy, right, that is produced by these events. And and if this is actually the amount of power is roughly 10 times the power produced by all the stars in the entire visible universe, right? It's that much of power. Now, but the power was all in the form of gravitational waves. So that is the problem, right? So it has huge power, but it is in the form of gravitational waves. Because of that, this is invisible to our instruments, except to this LIGO instrument or the laser gravitational wave observatory, right? And here are the result of that particular experiment. Now, actually, they had two gravitational wave detectors in two places in USA. As far as I remember, one was in Louisiana or somewhere like that. The other one was in a state called Washington. And the reason that they had all these the two locations, because if one detector did, they expect after some time, because when the gravitational wave travels in the speed of light, they can calculate how long it will take to go into the other detector, right, depending on the distance. So they expected that the other instrument also should detect the same thing after a certain time. So so this, the graph that you see in this left hand side, the first one right here is from one detector, and the second one is from the other detector after some time. So they can shift the two waves and see whether they are similar or not. Now, this is what they have done in this third one, and you can see that this yellow one and the blue one exactly matches, right? So there are only few differences. So for example, these large amplitudes are exactly matched together. So when they are shifted, which confirm them that they have detected these gravitational waves, right? So this is the short story behind this, and they actually got this Nobel Prize in 2017 for finding these gravitational waves. Now, actually, we have maybe a lot of detections of gravitational waves after that, and this particular setup basically explains you like how they are detected with these. Here is the like the diagram that you have a laser of the laser interferometer. So there is, this is one of the arms and this is the other arm. You can see that each of them are like 4 kilometers long, so that you send a beam and then you reflected it from there, and both these beams are collected and then sent to a detector right here, and depending on the interference pattern you can detect it, right? So that's what has happened. Now, actually, even after that, in 2019, the scientists were actually able to uh, create an image of a black hole. So this is the supermassive black hole of M87 galaxy, which is from the Event Horizon. There is a telescope called Event Horizon Telescope, which is not actually one telescope. It's a collection of set of telescopes that operates together to make this black hole. I guess sure the time. What time is now? Yeah, I guess we are close to the end of the lecture, so I will briefly explain this. And so here are some. There is a video as well. If you, I mean, once you convert this image or this gravitational waves into sound waves, you should be able to see it. And I'm not sure whether you can hear it or not. So just have a look at when you have this PowerPoint presentation, right? So you can check it yourself. So I'm not going to explain it. Right. So we have finally come to the end of this process of star formation now. And this one slide at the end, I will just summarize in all the end states of stars, right? So remember, we started from these main sequence, and then depending on the masses, we had different endpoints for different stars, right? Now the first one was the white dwarf, which is for white dwarfs, when they are in the main sequence, they had the mass less than 8 solar masses. So all the stars which had less masses less than 8 solar masses will become white dwarfs at the end. And when they become white dwarfs, their final mass will be less than 1.4 solar masses, right? So that is for white dwarfs. And for the neutron stars, in the main sequence, when you have stars between 8 solar masses and the 25 solar masses, and you know that during the process of this stellar evolution, they undergo significant amount of mass loss, right? Because of these different reactions. Their final mass will be between 1.4 and 3 solar masses. I mean, remember that these are not like exact numbers, but just to give you a good idea what we have discussed. So I have put this particular slide, and so those will become neutron stars. Now then stellar mass black holes, when you have stars that have main sequence masses greater than 25 solar masses, their final mass, as we discussed today, will be more than 3 solar masses. So if that is the condition, then they will become black holes, right? So that's what will happen. So this will actually finish our section about the stellar star formation. Now, I just put some of these, one of these myths and truths about the black holes. So sometimes you probably see that the people used to tell that the black holes go about sucking things up with their gravity, right? So they will go and attract and suck everything, but it's not true. That the truth is actually only very close to a black hole that this strange effects we have been discussing come into play. So you have to go into very close to a black hole for this to happen, right? So that is what you should know. Right, so this will end up this particular section about the star formation, and there is one section that I need to talk about binary stars, which I will take as the first one in the next day.